So in the last video we defined the subspace topology. Now we want to establish certain properties of that. The first one I want to talk about is about the inclusion map. Okay, so let's just recall the situation. So we've got let X be a topological space and Y a subset, and we give Y the subspace topology, i.e. V in Y is open in Y if and only if there exists U open in X with Y equal to V equal to U intersected with Y. Okay, that was the definition of the subspace topology. We define I from Y to X to be the inclusion map, i.e. I of Y is just equal to Y for all Y. So it's just like the identity map, but we take the domain to be Y and the codomain to be X. And so the first lemma is just that I is continuous. Okay, so this, okay, so what does that mean? Remember we're dealing with topological spaces. In the context of topological spaces, the definition of a map being continuous is that the pre-image of any open set should be open. So I have to say let U be open. Show that I inverse of U is open in Y. But what is I inverse U? That's the set of Y in Y such that I of Y lies in U, but that is just equal to Y intersect U, and that's open by the definition of the subspace topology. Okay, so there's really nothing going on in this proof, it's just the definition. So now let's consider a sort of related situation. So let's suppose we've got a map function, say f from X to Y of topological spaces. And then suppose we have subsets, say x1 contained in X and y1 contained in Y. And therefore inclusion maps, say I from x1 to X and J, say, from y1 to Y. And we give x1 and y1 the appropriate subspace topologies. And let's suppose also that this function f, okay, also f is sending X to Y, so we can apply it to this subspace, so all the points in the subspace xy, x1, and let's suppose that they're all contained in y1. That means you have a restricted map, which we could call f1 from x1 to y1. And that means we've got this diagram, right? We can got x1 here going by f1 to y1. Then we've got this inclusion map I here to X, and this inclusion map J here to Y, and then the original map F here. So firstly, I want to claim that if f is continuous, let's say if f1 is continuous, and so is J composed of f1. And if f is continuous, then so is f composed of I. And so both of those is kind of very straightforward, but also the point that's kind of I think it's a bit more point to it, like this. Thirdly, if J composed with F1 is continuous, then so is F1. Okay. Okay. So here, so here we sort of assume that F1 was continuous, and then J composed with F1 is continuous, or if F is continuous, then F composed with I is continuous. Those are both pretty clear, but slightly less obvious that if this composite here is continuous, then the F1 we can kind of go backwards, and A and B, we know that I and J are continuous by the lemma, and composites of continuous functions are continuous. And claims A and B follow from that. The proof of C, that's a tiny bit more to say. Okay, so let's say suppose supposing that J composed of F1 is continuous. Okay, and now we want to prove that F1 is continuous, so let's let V1 be a subset that's open in Y1. So we want to show that F1 inverse of V1 is open in X1. And now we know that Y1 has the subspace topology. That's how we set things up at the beginning. Y1 was a subset of Y, and we want to give it the subspace topology. And V1 is open in Y. Y1, therefore V1 has got to be equal to V intersect Y for some V that's open in Y. But also remember that this V because this J is just an inclusion, V intersect Y is the same thing as J inverse of V. V1 is J inverse of V. So that means that F1 inverse of V1 is F1 inverse of J inverse of V, which is J composed of F1 inverse of V, which is open because J composed with F1 is continuous by assumption. Okay, so that's all we had to prove, that F1 inverse of V was open, but it is because it's the same as J composed with F1 inverse of V. Okay, and then we'll have some further properties of the subspace topology in the next video.